Alright, so we are live with participant discussion and I'll be taking care of physics. Alright, so just taking some time so that everyone is on board and then we'll get started. So this is just a test. I'm going to see if it works or not. Alright, so it's about time and just waiting for everyone to join in. So just let me know if my voice is clear to everyone, and if you join, just say hi on the chat, live chat. Alright, so just let me know if you're here. Alright, so I'll wait for a few minutes and let everyone join. All right, few more minutes and then we can get going. Okay, so before we start, I just want you to tell me which what was your overall feeling about this paper, as in the difficulty level, and which topics were there where you faced difficulty especially. So I can focus more on those topics. Okay, you can just type it here so that I know where the main problem is. All right, so am I audible to everyone? If yes, just type it here. We're going to start in a minute. All right, so let's get started. A few things about things about this paper. So what I feel is this paper was sorry, a little bit on on the difficult side, and I won't say difficult, but it's more tricky. And if you start solving in the usual manner, it might take some time. But if you pay attention and if your concepts are clear, you can solve it in just 1 or 2 lines, and I'm going to show that to you. All right. Another thing is I'm not going to spend a lot of time on very simple questions, straightforward. I'll just give you a hint and move on so that I have a fair amount of time for the good questions and the difficult questions. All right. So let's get started. I'm going to start with the first. Alright, so let's get started, and I'm going to start with the first question. Okay, so this one is a fairly straightforward question. So the relative density has to be found, and what is given is I've been given the weight of the body in air, the weight of the body in water, and then I have to find the relative density of the liquid. So the formula is also given to me. So now you see there are two sort of operations happening here. So one is W1 minus W2. So whenever any operation happens, the error propagates, and we need to find that error before proceeding to the next operation. So the first thing we are going to do is, first of all, we are going to find W1 minus W2. So let's call that quantity X, and X is W1 minus W2. So 8 minus 6 is going to give me 2.00. But remember that the error propagates in a manner which only increases. The error can never decrease. Alright, so the error 0.05 here and the error 0.05 here, they are going to get added and not subtracted. Alright, so the error now will become 0.10, and that will be the quantity X, which is W1 minus W2. Now how do I find rho? The way to find rho is W1 divided by X. Now this quantity is rho. Alright. Now this quantity I can write it as W1 to the power 1 and X to the power minus 1. Okay. Now the way to find fractional error is, and probably you know this, delta rho by rho will be equal to delta W1 divided by W1, but we have to be careful that all of this I'm going to put under a mod, because the error never reduces, the error always increases. Alright, so plus I'll also put a mod over here, and this will become delta x divided by x. Alright, now that will be the expression for the error in measurement of the relative density. Alright, so all I need to do is put in the values over here. So what are the values? W1 has an error of 0.05, and the quantity W1 is equal to 8. So that I'm going to put it over here. Plus, what is delta x? Delta x we have found out, and that is 0.10. That I'm going to write over here, and then the value x is 2.00. Alright, now this is fractional error, but what is required is percentage error. So I'm going to multiply that by 100, and if you do these calculations, you'll find out that D will be the correct answer. Alright, just another tip, uh, if you understand this, that whenever you do any operation with these quantities, the error only increases, it cannot decrease. So just think about W1. W1 has an error of about 5 upon 8%, so that's close to 0.62%, and W2 has an error of 5 by 6%, and that is about 0.8%. So an error of 0.6% and error of 0.8%, when any operation is done with them, the error can only increase. So none of the options over here is above 0.8. So the only option you have is 5.62. So even without solving this question, you could have got the right answer. Alright. So I'm just going to see if there is any problem with this question, and then we can proceed. Alright, so if you face any difficulty, just write your comments in this live chat, and I can cater to that. Alright, so that is question number 1. Let's proceed to question number 2. I'll just grab a new board, and get started. Okay, question number 2. So a ball is projected from origin with this speed at an angle 30 degree with the x-axis. The x-coordinate of the ball at instant when the velocity of the ball becomes perpendicular to the velocity of projection. So basically what is happening is a ball is being projected like this. So this will be its initial velocity and it is projected with some angle theta. Again, it has some velocity u. Now, at some instant, the velocity will become something like this. Now, if you observe, the velocity vector here and the velocity vector here will become perpendicular at some instant. Alright, and we need to find out what will be the x coordinate at that instant. Okay, so the way to do it is, if we find the time at which the two velocities become perpendicular, then we can find out this x component of the displacement. Alright, how do we do that? We can do that by a very simple method, and that is using vectors. So u, I can write it as, the initial velocity I can write it as 20 cos, so the angle of projection is 30, so 20. Alright, so let's get started again. Okay, let's go back. Okay, so I'll just say all the things again, which I said probably you did not get it. Alright, so the velocities will become perpendicular. Okay, so u, the initial velocity, I can write it as 20 cos 30 I cap plus 20 sin 30 j cap. Now the velocity, now this is the final velocity, and that I can write it as 20 cos 30 I cap, because the x component of the velocity does not change. But the y component of the velocity will certainly change, and that will be 20 sin 30 minus gt. So that is basically what I have done is v is equal to u plus at. Alright, and that is the initial velocity in the vertical direction, 20 sin 30, and the acceleration here is minus g. Alright, now what we know is, if we do a dot product of u and v, alright, if we do a dot product of u and v, and both these velocities have become perpendicular, so obviously the dot product should come out to be 0. Alright, so what I'm going to get is, I'm going to get 20 square cos square 30, then I'll get 20 square sine square 30, and then I'm also going to get minus 20 sine 30 into gt. Alright, so that will be the dot product. Okay, if that is the dot product, I can make it equal to 0. Is that right? Okay, so when I have made it equal to 0, now all I need to do is I need to do a little bit of calculation, and then from there I can find t. Okay, so I can get rid of this 20, I can get rid of this 20, I can get rid of this 20 over here, and what I'm going to get is 20 cos square 30 plus 20 cos square 30 is going to give me 20, and then sine 30 is half. So I'm going to get t is equal to 4 seconds. Alright, just a little bit of calculation over here. So if I get t is equal to 4 seconds, now all I need to find out is x. So how do I find out x? X will be equal to u cos 30. So 20 and cos 30 is going to be root 3 by 2, because the horizontal component of velocity does not change. So I could directly write x is equal to ux multiplied by t. Alright, so this gets cancelled and I'm going to be left with 40 root 3 meter. Alright, so 40 root 3 meter, so A is going to be my answer. Alright, let me see if you have any difficulty here. Alright, good. Now let's proceed to the next question. Let me get the new board. Alright, let's get to the next question. So now a question on electrostatics. Fairly simple question. Alright, I'm going to deal with that very quickly. Okay, so what we have is we have 3 plates. Okay, drawing with this pen is a little bit difficult. Anyway, I'm going to try. So there are 3 plates. This plate has been given a charge q, this plate has been given a charge minus q, and then a plate q, charge q is inserted between them. Alright, now it is given to us that all these A and B plates are isolated. Isolated means they are not connected with anything else. Alright, and so the plate C, which is inserted between them, is also isolated. Okay, now how do we proceed with this question is that the field inside the conductor is always 0. So the field inside the conductor will be 0, inside this conductor will also be 0, and inside this conductor will also be 0. So for that we already know that on the surfaces facing each other there is always equal and opposite charge, because if I draw a Gaussian surface like this and there is no field over here and there is no field over here, and the field is going to be perpendicular to this surface, so the net flux through this Gaussian surface is going to be 0. So whatever is the charge here, I'm going to get, so suppose if I have plus q over here, I'm going to get minus q over here. That is absolutely necessary to have. Alright, so the charges, so the plates facing each other are always going to have equal and opposite charge. Alright, so what happens because of that is the net charge, so plus q and minus q will cancel each other out. Similarly, plus q and minus q will cancel each other out over here. So what you're going to be left is the net charge on all the 3 plates combined is only going to appear on the outer surface of the outer plates. Alright, and they're going to get distributed equally on the outer surfaces. Why? Because only then they can cancel out the field inside the conductor. Alright, so the net charge on all the 3 plates combined is equal to q. So q by 2 is going to appear here, and then q by 2 is going to appear here. Alright, let me grab an eraser and rub this off. Alright, now what we need to understand is that this plate is isolated. If it is an isolated plate, the net charge on it has to be conserved. So the net charge is q and it has to remain q. So if there is q by 2 charge on this surface, there will also be q by 2 charge on this surface. Okay, and then if there is q by 2 on this surface, there has to be minus q by 2 on this surface. Alright, now again this charge is q and this plate is isolated, so the net charge should still remain q. Okay, so if there is minus q by 2 charge on this surface, there will be 3q by 2 charge on this surface, and this surface again will have an equal and opposite charge. So this is going to be the final charge distribution on all the 3 plates. Alright, now it is not very difficult to see the options. The first surfaces 1 and 2 will have equal and opposite charges, absolutely correct. The surfaces 3 and 4 will have equal and opposite charges, absolutely correct. So this is also right. The charge on surface 3 will be greater than q. So this is surface 3 and the charge on it is 3 by q by 2. So that is also correct. So naturally the correct response here would be D, which is the wrong statement. Okay, the potential difference between A and C is equal to the potential difference B and C. Alright, and that is absolutely incorrect, because the field would be in this direction over here and the field would be in this direction over here. So going from here to here, we'll have a potential drop, and then going from here to here, we'll also have a potential drop. Alright. So the potential difference between A and C cannot be equal to B and C. Alright. So the right answer is going to be D. Alright. So far so good. Alright. So we're going to move to the next question. Okay, so question number 4. A particle starts its motion from rest, moves with a constant acceleration for time t1, and then it retards with constant rate for time t2 until it comes to rest. Then the ratio of maximum speed and average speed during the complete motion will be. Alright, now you can use your equation of kinematics, uh, all the three equations of kinematics to solve this question. That is not a very difficult thing. But what I want to show you specifically is how you can solve this question with graphs. Alright, and graphs are a very handy tool in kinematics, especially whenever we are dealing with velocity and time. Okay, so I'm going to show you how we can solve this by the graphical method, and that will be a much easier and much faster method. Alright, so let's get started. So it moves with a constant acceleration. So constant acceleration means it will be a straight line on the VT curve, and this time interval will be t1. Now it retards again with a constant velocity, constant retardation. So this will also be a straight line, constant slope, and this time interval will be t2. And let's say this is the maximum velocity it has reached. Okay. Now how do we find average velocity? The average velocity is equal to the displacement divided by the time interval. Alright. Now how do we find displacement in the VT curve? The displacement in the VT curve is the area under the curve. Alright. So that is a triangle, and I can write that triangle as half into the base. The base is t1 plus t2, and the height is v naught. Is that right? The height is v naught. Okay. Now we need to divide it by the time interval. So I'm substituting for t. So what is the time interval? The time interval is t1 plus t2. Okay. So t1 plus t2 gets cancelled. T1 plus t2 get cancelled. So what I'm left with is v average. Or what do I need to find out? I need to find out the ratio of maximum speed to the average speed. So basically what I need to find out is V naught divided by V average, and that is going to give me 2:1. Alright, so your answer is going to be A. Okay, so you see that using graphs you can solve a question which will take much less time than you would have used the equations to solve this question. Alright, any difficulty you can just write it here and I can address that. Okay, then let's move forward. Another board. Okay, let's get to question number 5. Now question number 5 is again a very easy question on errors, and I'm just going to give you the hint and move on, and this is a fairly simple question. Alright, so the length is 20.0 centimeter, and the time interval for 100 oscillations is 90 seconds, and the resolution of the stopwatch is 1 second, and we need to find out the error in determination of G. Okay, so how do we do that? First of all, if I am writing L is equal to 20.0 centimeter, now what does it tell me about the error? Now this is 20.0 centimeter, so it is pretty obvious that the least count for this measurement would be 0.1 centimeter, because I have one digit to the right of the decimal. Alright, so it can only be measured by an instrument which has a least count of 0.1 centimeter. So generally what we take is the error for any measurement is equal to the least count of that instrument. Alright, so L I can write it as 20.0 plus 0.1 centimeter. Now what about the time period? Now the time taken for 100 oscillations is 90, and the resolution is 1 second. That means that the least count is 1 second. Alright, but this is the time taken for 100 oscillations. So what will be the time period? I have to divide it by 100. So what I'm going to get is, I'm going to get 0.9, it should be plus minus 0.01 second. So basically what we have done is, if we take a lot of uh, so if we are taking the time taken for more oscillations, I can reduce the error. So if I had just taken the measurement for one oscillation, I would have had an error of 1 second. Alright, but now what do I have? I have an error of 0.01 second. Alright, so we know that time period is equal to some constant into under root of L by G. So that is going to give me G is equal to L T minus 2 and some constant. Alright, now it is not very difficult to see that you can find delta G by G is equal to delta L by L in a mod, again in a mod, because the error only increases, plus 2 times delta T by T again in a mod. Alright, and we know all these values. So delta L is 0.1, L is 20, delta T is, excuse me, delta T is 0.01 and T is 0.9. So if you calculate this, I hope you're going to get 3% as the answer. Alright. Yeah, so the meaning of 1 second resolution is that it has the least count of that instrument is 1 second. Alright, so it will have all the dials separated by 1 second. That is the meaning of resolution being 1 second. Okay, let's move forward again. Okay. Okay, let's move forward. So this question number 6, what do we have? We have a projectile on an inclined plane. Okay, the question here is P is projected, alright, and simultaneously Q is released, and after 4 seconds both of them collide. Okay, and then we need to find out the speed of projection of P. How do you solve questions on projectile on an inclined plane? The general method is to just tilt your axis. Alright, all you need to do is tilt your axis. Okay, so what I'm going to do is I'm going to make this the x-axis, I'm going to make this the y-axis. Okay, because the motion is happening in the xy plane, which is a bit tilted with respect to the horizontal. So I'm going to use this coordinate system to solve this question. Okay, now the question is, when P is projected, it is going to have some velocity, let's say Vy, and it is going to have some velocity Vx. Okay, so that is P, and then Q is released from here, and then when Q reaches over here, at the same instant P also reaches here. Okay, now you can solve this question by resolving all the velocities and accelerations along the inclined plane and perpendicular to the inclined plane, and you can do it with the usual manner how you deal with projectile on the inclined plane. But what I'm interested in is how you can solve this question in just a couple of steps. All right, and if you understand this very clearly, you can solve these kind of questions in very less time. All right, if you use what I'm going to tell you. Okay, now what you're going to realize over here is Q and P. Okay, so let's just talk about the motion of Q along the inclined plane and the motion of the only x component of motion of P along the inclined plane. Okay, I'm only interested in these two quantities. Okay, now they cover the same displacement in the same time interval, and the acceleration of the particles is also same along the inclined plane. All right, and that is going to be say if this is G, this angle is 60 degree, so this angle is going to be 30 degree. Okay, so the acceleration perpendicular to the inclined plane is going to be G sine 30 degree, and the acceleration along the inclined plane is going to be g cos 30 degree. Okay, now what you should realize is the displacement, the x component of the displacement is same for p and q, the time taken is same for p and q, and also the acceleration is same for p and both p and q. So what does that suggest? It suggests that both of them are going to have the same velocity along the inclined plane, same initial velocity along the inclined plane. All right, and what is the velocity of q along the inclined plane? It is zero because it is released from rest. So what does that tell me? It tells me that Vx is equal to 0. Alright, and that is the critical part which you need to understand. Now if you understand this, uh, the velocity, finding the velocity is very easy. Okay, so if you're convinced that Vx will be equal to 0, then it only has, P only has a component which is perpendicular to the inclined plane. Okay, now if you have already tilted the axis, you can understand that the time of flight is always 2 into Vy divided by the acceleration. Alright. Now the difference here is the acceleration is not g, but the acceleration here is g sine 30 degree. Alright. In the perpendicular to the inclined plane direction, the acceleration is g sine 30 degree. Alright. So all I need to do is modify g by g sine 30 degree. Alright, and that is how we can write the expression for the time of flight. Okay, so what is the time of flight? The time of flight is given to us, which is 4, and this will be equal to 2. And what is Vy? Vy is something we need to find out. Divided by g is 10, and sine 30 degrees half. Okay, so if you do the calculations, Vy will come out to be 10 meter per second. Alright, so you see that we have not employed any difficult concept of motion along the inclined plane perpendicular to the inclined plane. The only thing is, if two particles are colliding, what can we infer from that? Alright, so they have equal displacement, equal time interval, and equal acceleration implies equal velocity, initial velocity. Okay, using that we can solve this question very quickly. Okay, so I have a question here. Sir, if there were two decimal places, then error will be 0.01, right? Yes, absolutely. You are absolutely right. Okay, so I hope this question is clear. Appears difficult, but if you think it through, it's not very difficult. Okay, let's move forward. Okay, question number 7. So a block B is floating in the river. Okay, so this is block B floating in the river. The position of the block is shown in the figure. So this block is 40 meter from the bank, and the river is flowing with a velocity 2 meter per second. A stone is thrown with a velocity Vi, V1, V2, V, and then 20k, such that the stone hits the block. The value of V2 is, okay. Again, uh, let me try and redraw this over here. So this block is over here. Okay. Now the block cannot does not have a motor, so it is going to flow along with the river. So the block is going to move along the river with a velocity of 2 meter per second. All right. Let's say when it reaches at this point. Now the stone projected has three components of velocity. It has, let's say, Vx, it has Vy, and there is also Vz coming out of the plane of the board. Alright, so it is projected, so it's a projectile. But what I know is it hits it over here. So it will go in the air and then it is going to hit it over here. Okay. Alright. What we need to understand over here is that the x component of displacement, only the x component of velocity is responsible for that, and the y component of displacement, only the y component of velocity is responsible for that, and similarly for z. Okay, so all the three velocities and the three components live their own lives, and they are not dependent on each other. we can use that fact to solve this question very easily. Okay, how we can do that is, so what I have been given is the river is flowing at 2 meter per second. Okay, now the the x component of the displacement of the block and the x component of the displacement of the ball aren't the same. Okay, so this is the displacement of the stone. Alright, but what is the x component? This is the x component of the displacement of the stone, and this is the x component of the displacement of the what do we have? The block. Alright, so what we can say is the velocities of the block and the x component of velocity is going to be the same. Alright, so from there we can say Vx is equal to 2 meter per second. Alright, okay, but what we are interested in? We are interested in okay, stone is thrown. Okay, so we are interested in finding out V2. So what we have been given is we have Vz. Alright, so Vz is given to us, and that is 20 meter per second. So we have Vz is equal to 20 meter per second. Okay. Now if I have to comment on the time of flight, alright, how much time does it take to hit this block? So the time of flight only depends on the vertical velocity. Alright, we know that already. So at half the time of flight, the vertical velocity becomes 0, and it takes the same amount of time to come down again. Alright, so the time of flight will be equal to 2 into Vz, because that is the vertical velocity, and the time of flight only depends on the vertical velocity and nothing else. And the acceleration will be the acceleration due to gravity, and let's say that will be 10. Okay, so this will be equal to 2 multiplied by Vz. What is Vz? Vz is 20 divided by 10, so that is going to give me 4 seconds. Okay, so we have already found out what will be the time of flight and what is the time taken for this motion. Okay, and that is going to be 4 seconds. Now if 4 seconds is the time taken for this ball to hit this block, 4 seconds is also the time for the completion of its y component of the displacement. Alright, so can we write Vy will be equal to the y component of this displacement, and what is the y component of displacement? It is 40, and then divided by the time taken, which is 4, so that will be equal to 10 meter per second. Alright, okay, so I have a question over here in question number 6. If P was not projected perpendicular to the inclined plane, then will they collide? Absolutely not. They are not going to collide, because if it was not projected perpendicular, it will have a component of velocity along the inclined plane. Okay, and rest of the things remaining same. If the initial velocity along the inclined plane is not same for both the particles, they are never going to collide. Alright, you are absolutely right. Okay, now this question again looks complicated, but if you break it down and think it through carefully, again it's not a very difficult question, and you can solve this in 1 or 2 steps only. Okay, and we want to move forward now. Let me get rid of this, also this, and also this. Okay, so now we are at question number 8. Three particles move in a straight line. Okay, so they are moving with velocities v1, which is less than v2, which is less than v3, each with constant retardation a, such that the motion continues for more than 1 second before the velocity of each particle becomes 0. If s1, s2, and s3 respectively be the distances traveled in the last 1 second before velocity becomes 0, then okay. Now again, what you can do here is you can employ your formula for s nth. All right. So the displacement in the nth second, and that displacement in the nth second is equal to u plus half into a into 2n minus 1, where n is the second, the nth second. Okay. If you try and solve this, you can certainly solve this question, but again, What I want to focus on is the graphical method to solve this. And if you try to solve it graphically, again, it becomes a very, very, very easy question, and you can solve it in probably 30 seconds. Okay. So what I'm going to do here is I'm going to draw a VT curve. Okay. Now the retardation for all of them is same. So let's say the first particle, and this is V1, and its graph is going to be like this. Okay, constant retardation, so the slope will be constant and negative. Okay, v2, the graph for v2 will be something like this. It starts with velocity v2, and then graph for v3 will again be something like this. Okay, but what we are asked is, okay, another thing to note over here is all these three lines are going to have the same slope because the retardation is the same for both of them. Alright, so all these are basically parallel lines. But what we are interested in, the displacement in the last 1 second only. Okay, so let's say this is 1 second. Let's say this is 1 second, and let's also say this is 1 second. Okay, so what we are interested in, this area and this area. So these area would be S1, S2 and S3. Alright. Now since this is all 1 second and the slope is also constant, so this length and this length will also be the same. Okay. So what can we conclude from here? That the area 1. Alright, so I think again it got disconnected. Anyway, we are back. Okay, yeah, I have a few questions. Let's look at that. Okay, so question number 7, how the stone will hit the block. The block is in xy plane and the stone has a z component of velocity. Absolutely. So the x component is along the river, the y component is perpendicular to the river, and z component is vertically upwards. So if something is thrown like a projectile, it will come back to the ground again, and that's why it is going to hit the block again and reach the xy plane. Alright. So yes, Raj has correctly got it. The z component also has an acceleration due to gravity. You're absolutely right. Okay, I have another question. What is the meaning of line of motion continues one last second? I'm not sure if I saw that somewhere. Uh, if you mean that the motion continues for more than 1 second, probably that's what you mean. Okay, so basically the question is, what is the displacement in the last 1 second? So if we want to find that out, obviously the particle has to move for a time which is greater than 1 second, and that is the meaning of this statement probably. Okay. So yeah, we can move forward. Okay, so question number 9. Let's look at question number 9. Okay. Okay, question number 8. Yeah, go ahead. Yeah, probably I answered your question. All right, great. Let's move ahead. So let's go to question number 9 and So a point moves in a straight line under the retardation AV square, where A is a constant and V is a velocity, then distance covered in t second is. Okay, this is a question which probably needs a little bit of brute force to solve it. Alright, uh, so acceleration is given to us minus alpha v square. So this a, I'm changing that to alpha to avoid confusion. So a is equal to minus alpha v square, minus because it is retardation. Okay, uh, I'm just going to tell you what is the method you can employ to solve it, and it's a bit tedious, but nevertheless it's not difficult. All right, so dv by dt I can write it as minus alpha v square, then dv will be equal to minus alpha, so dv by v square will be equal to minus, all right, and this you can integrate within proper limits, so 0 to t, and then this you can integrate from v naught to some t. Okay, we can do that. Sorry, v naught to, let me just change this, v naught to some velocity v. So from here what you're going to get is you're going to get velocity as a function of time, but what we need is displacement as a function of time. So again you're going to have to write dx by dt is equal to whatever you have found it over here, send dt that side, integrate again, and you're going to solve it. Okay, so I don't see any shortcut method to solve this question. It has to be integrated twice. Okay, so this is a kind of question which is fairly simple, but it is time consuming. So my suggestion would be spending 30 seconds, 40 seconds into this question. You should move on. All right, you should not spend so much time. You should mark it and move ahead. And if you get time, you can come back to this question, because there is a surety you will be able to solve this question. All right. So yeah, that's all I need to tell you about this question. All right, let's move ahead. Okay, so we have a question on screw gauge. So probably you know how the screw gauge works, and if you don't know, I would suggest you should be well versed with this chapter. All right, so because there is a question on screw gauge or vernier calipers every year, both in main and advanced. All right, so this is very simple chapter and it should not be neglected. Okay, so what do we have here? The circular scale of the screw gauge has 50 divisions. All right. The pitch is 0.5 mm. All right. So what is pitch? Pitch is the complete rotation of the screw and the distance moved ahead by the cap scale, or this cap. All right. This circular scale, that is known as the pitch. Find the diameter of the sphere. Main scale reading is 2. Okay. Now this is the initial condition when there is no object inserted between the jaws. Okay. What you see here is the 0 does not coincide with the 0 of the circular scale. That means this has a 0 error. Alright. So how do we solve this, or how do we find out the reading of uh, screw gauge? Okay, first of all, what we need to find out is the least count, and the least count of screw gauge is defined as pitch divided by the number of divisions on the circular scale. Okay, that is how we define pitch. So how least count? All right, so the least count is going to be 0.5 mm divided by 50. All right, so that is going to give me 0.01 mm. All right, that will be the least count of this instrument. Okay, but this instrument has a 0 error, and we need to find that 0 error. All right, so how do we find 0 error? So basically 0 error is nothing but the reading at this instant or at this position. Okay, now you see that the fifth division of the circular scale coincides with 0, so it is ahead. So this is known as positive 0 error. Okay, so what is the main scale reading? The main scale reading you can see here is 0. Alright, so the main scale reading is 0 plus, what is the circular scale reading? Circular scale reading is the coinciding division of the circular scale multiplied by the least count. So that is going to give me 5 multiplied by 0.01. Okay, so that is the 0 error, and 0 error is positive. Now let's come over here and then find the reading over here. Okay, so what will be the reading? The reading is this main scale reading. And what is the main scale reading? The main scale reading is 2. Now this is not 2 mm. See, there is no mm attached to it. So the main scale reading being 2 is the number of divisions. Okay, so each of those divisions is how much? Each of those divisions is 0.5 mm. Alright, which is the pitch. Okay, so what will be the main scale reading? The main scale reading would be 2 into 0.5 mm. Okay, so that is going to be 1.0 mm plus the coinciding division. What is the coinciding division? 25 multiplied by what is the least count of the instrument? The least count of the instrument is 0.01. Okay, now that is the reading, and the reading comes out to be how much? The reading comes out to be 1.25 mm, and the zero error comes out to be 0.05 mm. Okay, now the final reading is always the reading minus the zero error. The zero error is always subtracted. Okay, so if you do a subtraction over here, you can see that 1.2 millimeter will be your answer. Okay, now you might have a question. All right, so this will come out to be 1.20 mm. Okay, so you might have a question that the answer should be 1.20 mm, but the answer given over here is 1.2 mm only. Okay, and that has to be with because of the significant digit. All right, so what is, if I'm writing 1.20 mm, that means the least amount of measurement I can make is 0.01 mm. Is that right? Okay, but what is the least count of the instrument? The least count of the instrument, uh, okay, it's 0.01 mm. So that's fair enough. That is fair. So the answer should have been 1.20 mm. Yeah. So A will be the answer. Anyway, that's the only option that matches. So A will be the answer. Okay, I have a few questions again. In question number 9. Okay, so where is question number 9? What is U in the option? Alright, so U, if nothing is given, will take it as the usual convention. Alright, so U is stands for, generally in kinematics, it stands for the initial velocity. Alright, and probably that will be U. So what we have used V naught over here, probably that will be equal to U. Okay, so if nothing is given to you, uh, all we are going to do is we're going to use the usual meaning of those symbols. Alright, so U here would be the initial velocity. Okay, so I have another question. What is exactly the meaning of pitch? Yes, you can say that. You can say that. So if you rotate the screw gauge completely, the circular scale completely, if you make it go by one complete revolution, it is going to advance with the amount it advances with is known as the pitch. And generally, the pitch is also the equal to the main scale division. All right, one main scale division. So yeah, you're right over here. All right, we can now move forward. Let's. So 10 is done. All right, 11. Any questions? No, we're good. All right, let's go to question number 11. The question number 11, what do we have is, there's a 2-meter wide truck is moving with a uniform speed 8 meters per second along a straight horizontal road and pedestrian. Okay, this guy is going trying to cross it. The minimum constant velocity with which he should run to avoid an accident. Okay, now the tricky part here is minimum constant velocity. Okay, so your answer is not going to be, so generally if you're going to solve it, probably you would have done this. So time taken for the truck to get to that vertical line would be equal to what, 4 divided by 8, and that is 0.5 seconds. And in those 0.5 seconds this guy has to move to the other side, so you will be equal to the distance it has to move in that direction, which is 2 meter, divided by the time. So that will turn out to be 4 meter per second. Alright. So probably a lot of people would have done this, but if you see, there is no option matching. Okay. And if the question setter, the person who is setting this question, were not very considerate, the first option you would see would be 4 meter per second. And most of the people would have got that wrong. Okay. But the tricky part here is it moves with a constant velocity which is minimum. It has to move with the smallest possible velocity it can. Alright. So basically, if you use common sense, okay, if he has to move slowly and reach that point, he is never going to take this path. He is never going to take this path. Alright. So if he wants to move with constant velocity, minimum constant velocity, he should avoid the truck as far as possible. So what he's going to do is he's going to move along this line, okay, which is going to be slightly in a diagonal manner. Alright. Now let's say he digresses from his path by a distance x. Okay. Now this is, how much is this? This is 4. Alright. And this is 2. Okay. So actually what he is going to traverse is he is going to traverse a distance of x square plus 2 square, which is 4, and then the under root of that. Alright. So actually he should go something like this. Okay. Now what is the time taken? The time taken by the truck will be how much? The time taken by the truck to reach this point. So the truck is also not moving by a distance 4. The truck is going to move by a distance of 4 plus x. Alright. 4 here and x over here. Okay. So what we can say is the time taken by the truck would be equal to 4 plus x divided by the velocity, which is 8 meter per second. Yeah. That will be the time taken by the truck, and that will also be the time taken by this person, and the time taken by this person would be x square plus 4, which is his displacement, divided by his velocity, let's say, which is v. Okay, so what do we get? We get v is equal to 8 into under root of x square plus 4 divided by 4 plus x. Okay, that will be the velocity with which he should move. Okay, now we need to minimize this velocity, and in order to minimize this velocity, I hope you already know what is maxima minima. So differentiate this, make it equal to 0, find the roots, substitute, and you can find the minimum velocity. Alright, that part I'm going to leave it to you. Okay, so your answer will come out to be A. If you do the calculations, it should come out to be A. Let's see if there are any doubts. I think we're good so far. Let's get rid of this. Let's move forward. Good. Question number 12. So two vectors A and B are drawn from common point C is equal to A plus B, an angle between A and B. Alright. Now this is a very straightforward question, no brainer. Okay. So if they are at 90 degree, C square has to be equal to A square plus B square. So A will not be the correct option. If it is greater than 90 degree, C square should be less than A square plus B square. Alright. Naturally, if they are making an obtuse angle, the resultant would be lesser than C square. Alright. So this is fairly a straightforward question, a no-brainer. So B will be the answer, and I hope we can move forward. Okay, question number 13. Again, units and dimensions, a neglected chapter, but you should not neglect this because there is a question every year, and it's a piece of cake. All right. So x, y, and z are three physical quantities having different dimensions. Which of the following mathematical operations must be meaningless? Okay. So basically what we need to keep in mind is, if we are adding two quantities, they have to have the same dimensions, adding or subtracting. And if we are equating two quantities, both of them should also have the same dimension. So x by y is equal to z, it's possible x into y divided by x plus y. Okay, so x and y have different dimensions, so basically we cannot add x and y. Alright, so option B, that should be a meaningless quantity. Alright, I hope you don't have difficulties in these questions. Pretty straightforward. Alright, good. So question number 14, again very simple question, and I don't want to spend time on it. I hope you can do that on your own. Alright, so we're going to focus on more important questions. Alright, so let's look at question number 15. So there's a tunnel over here, and a point charge of mass m is projected with velocity v inside the tunnel as shown. The tunnel has been made inside a uniformly charged non-conducting sphere. Okay, so non-conducting sphere means that there will be the charge would be distributed uniformly along its volume. Okay, the minimum velocity with which the point charge should be projected such that it can reach the opposite end of the tunnel is equal to. All right, this is a fairly good question. Okay, but it's not very difficult to understand. Alright, let's look into it. Let me try and draw this. Okay. Alright, alright. Okay. What should also have been mentioned here is that the tunnel is very, very, very thin. Alright. So that even if there is tunnel going through this, it is not going to affect much to the overall charge on this or overall volume of this sphere. Okay. So it is being projected with a velocity v naught. Let's say with a velocity u, and we have to find minimum u such that it crosses the tunnel. Okay, so if this is positively charged and this this point charge over here is also positively charged, so if this particle is over here or anywhere before this point, the direction of the field would be something like this, and it is going to have a component opposite to this direction. Okay, so because of that, it is going to face some resistance going into the tunnel. Okay, but the thing over here is the velocity required is the minimum velocity. Okay, uh, so we don't need to apply energy conservation between this point and this point. Why? Because if it just crosses this point, let's say it reaches this point, okay, then the direction of the field would be something like this, and there will be a component of field along this direction. Okay, so if it crosses this point, it is automatically going to be pushed away from the center, or it is going to be pushed out of the tunnel. Okay, so it will automatically reach the opposite end of the tunnel. Okay, so all we need to ensure is it is projected with such velocity that it just reaches this point. Okay, and that's all we need to do to find this minimum velocity. Okay, and then we already know we can conserve mechanical energy and solve this question. Okay, so how do we do that? If you know that the potential due to a uniformly charged sphere, solid sphere, is given by k cube upon 2r cube, and then 3r square multiplied by small r square. So that small r square is the distance from the center. Okay, so we are applying conservation of mechanical energy between this point and this point. Okay, so the potential at this point will be equal to, let's say, the initial potential at the initial position will be equal to k cube by 2r cube, and then you can substitute 3r square, and you can substitute capital R for small r. So this is going to give me 3 by 2 k cube upon r. Okay. Similarly, what we can do is we can also find the potential at this point. Let's call that potential at the final point, and that potential at the final point will be k cube upon 2r cube, and then you're going to have 3r square, and then you need to substitute small r by 2. and that is given to us over here. All right, and the square of that. Okay, slightly cramped for space. I think I should use another board. Okay, but we know the potential, and what we know about potential energy is potential energy would be Q multiplied by the potential. Okay, so conserving mechanical energy, I can write Ui plus Ki should be equal to Uf plus Kf. Alright, what is Ui? Ui would be equal to Q multiplied by Vi. What will be initial kinetic energy? The initial kinetic energy would be half mu square, and that is equal to U final. U final will be Q equal multiplied by the potential at the final position plus K final. Now since the velocity required is 0, the minimum velocity required, so the final kinetic energy would be 0. That it just reaches this point. Alright. Now from there, what we need to do is we just need to find U. You can substitute all the values in Vi and Vf and you can find U. But if you observe, your options are in terms of rho. Alright, and that rho is the charge per unit volume. So all you need to do is Q is equal to rho multiplied by 4 by 3 pi RQ. Alright, so if you substitute Q by this quantity, and then you can do the manipulations and you can get the answer in this format. Alright, but that is the crux of this problem. So the only tricky part here is that in order to cross the tunnel, the minimum velocity required is only that much, which ensures that it reaches this point with 0 velocity or slightly more velocity than 0, and that's it. Alright, I hope everything is clear so far. So let's move forward. Let me grab a new board. Question number 16, that is also a very straightforward question, and I don't want to spend time on that. If you have a problem, you can just ask me or just write that in the chat and then I can discuss that. Okay, let's get to question number 17. So question number 17 is a little bit tricky. Okay, so what we have over here is, so this is the incident light, this is the reflected light, and this is the outward normal. So basically this is given to you as C, this has been given to you as B, and this has been given to you as A. Okay, so what we need to do is we need to find the relation, we need to find B in terms of A and C. Alright, so the way we can solve this question is something like this. Let's say, let me get rid of this. Why I'm getting rid of this, I'm going to tell you in a second. Let me make this clear again. Okay, now that this direction was A, so I'm going to make this as minus A. Alright, that's what I'm going to do. Now angle of incidence and angle of reflection is same, so both these angles would be theta, and this is C. Okay, now what we know is, since A and B both are unit vectors, these two magnitudes would be the same. So the resultant of minus A and B would be along C. That is also obvious. The resultant of two vectors equal in magnitude is along the angle bisector. Okay, so we can write it something like this. So the resultant of B and minus A is B minus A, and B minus A is going to be along C, but I am not sure of the magnitude, so I can write it as some constant multiplied by C. Alright, right. Then if we take a dot product on both sides, and what we are doing is basically we are taking a dot product with C. Alright, so this is going to give me C dot B, or we can do it the other way. We can do it the other way. So let's dot it here. Okay, sorry. Dot product with C and then dot product with C on both sides. So this is going to give me B dot C minus A dot C, and that is equal to K, and C dot C is going to give me C square, and which is, because the magnitude of C is 1, I'm going to get 1 over here. So basically what is K? K is equal to B dot C minus A dot C. Okay. What we can see from here is, because this angle is same, this angle theta is same, so we can say that minus A dot C, which will be 1 into cos theta, is also equal to B dot C, because that is will be also be equal to 1 into cos theta. So B dot C from here I can substitute with minus A dot C. So this will become minus A dot C minus A dot C, and that is equal to K. So this becomes minus 2 A dot C is equal to K. Alright, now this K we have found it here, this K we can substitute in this equation, this earlier equation that we had formed. We substitute it there, then make B the subject of formula, and then you're going to get the correct answer, which is D. Alright, so if you solve it with the usual method, it becomes a little bit difficult, a little bit tricky. Alright, but as far as this question is concerned and this option is concerned, you could have solved it with a little bit of use of elimination. Alright, and I'm going to show that to you. Okay, so what do we have here is, this is C, this is B, alright, and this is A, something like this. Alright, and let's look at all these relationships and try to find out if these relationships are possible or not. Alright, so B is equal to A minus C. Alright, B is equal to A minus C. So this is A, this will be minus C. So the resultant of A and minus C has to go between them, it cannot be B. Alright, so A is certainly not possible. Okay, let's look at other conditions. B is equal to A plus A dot C into C. So A dot C will be a constant. Okay, so that will be some constant into C. So this will be something like this, and this is A. Alright, so B is equal to A plus some constant into C. Okay, so this is A and this is some constant into C. So B, that might be possible. Alright, yes, that might be possible. Alright, so let's keep that in mind and let's look at other options. Okay, so I'm going to rub this again. Okay, let's look at option number C. So B is equal to 2A minus C. So this is A, so 2A would be something like this, and minus C, again minus C would be something like this. Okay, so the resultant of 2A and minus C has to go between them, it cannot be B. Alright, so option C also we can eliminate. Let's get back and let's look at option number D. So A minus 2A dot A into C. Okay, so A dot C into C is again a constant and negative of that. Okay, uh, so this quantity over here minus that should be something like this. I think we're making a little bit of mistake over here. So that is minus some constant into C, and then this is A. Just hang on a second. I think we're making some kind of mistake over here. So this is A, this is minus some constant into C. So the resultant of that cannot be B. Probably we are making some mistake. Let me check it again. Alright, let's take a new board. So this is C. B is the reflected ray, alright, and this is, so this would be the incident ray. Let's call that A. Okay, yeah, that's fine. So A dot C, so what is the angle between A and C? The angle between A and C you can see is obtuse. So A dot C is going to be a negative quantity. So negative of a negative quantity, so that will make it plus some constant into C. Okay, so some constant into C is going to give us this, some constant into C. So A and then some constant into C, and the resultant of that could be B. Alright, so option D is possible. And as far as option D is possible, and as far as option B is concerned, we can look at that also. Okay, now A dot C is, so the angle between A and C is obtuse. So A dot C is a negative quantity. So this term over here is going to give me something like this. Alright, now the resultant of A and minus Kc is never going to give me B. Alright, so using elimination also you could have solved this question. Okay, but the usual method is a little bit tricky. Alright, so we can move forward. Okay, no questions so far. Okay, let's take a new board and move ahead. Okay, so let's look at question number 18. A projection is aimed at a mark on a horizontal plane through the point of projection which falls 6 meters short when its elevation is 30 degree, but overshoot the mark by 9 meters when its elevation is 45 degree. The angle of elevation of the projectile. Okay, so looking at the options, looks like there has to be a lot of calculation over here. Okay, never mind. So let's say that mark is at a range R. Okay, so what it is told to us that if it is projected at an angle 30 degree, it falls 6 meters short. So R minus 6 will be equal to U square sine 2 theta divided by G. Alright, then when it is short at an angle 45 degree, it overshoots by 9. That means the range in this case would be R plus 9 is equal to U square by G multiplied by sine 90 degree. Alright, so for it to hit the range, which is R, it should be U square sine 2 theta divided by G. And that is what we need to find out. Okay, so this quantity theta is something we need to find out. So if you look at this question, we have three variables. One is R, the other variable is U square by G, and the other variable is theta. Okay, so basically this boils down to solving three equations to get the values of those three variables. Right, and you'll have to go through these calculations to actually find out the value of theta. All right, so there is nothing, no other innovative way to solve it. You have to solve using these three equations. All right, So it becomes a bit tedious, and as I suggested earlier, if you see a question is very tedious, you might just mark it and move ahead. And if you get time, you can come back, because there are a lot of questions waiting for you, which could be solved in much lesser time. All right. So that would be my suggestion. But as far as this question is concerned, it's not very difficult to solve. Just the calculation might be a little tedious. All right. So we are going to move ahead. All right. Question number 19. Which of the following lines may represent electric field lines? Okay. Uh, so there are a lot of properties of electric field lines. Uh, First thing we can see here is option number B. Alright, so option number B cannot be a field line, and that can be set straight away. Why? Because at this point where they are intersecting, alright, it is going to have, so we already know that the electric field lines cannot intersect. Alright, why they cannot intersect? Because if they intersect, they are going to have two directions, or they are going to have two directions of electric field at the same point, and which is not possible. So if we look at question number 8, option B, it is certainly not possible. Alright, so we can let go of option B. Let's look at question number option A. Alright, now you might be tempted to say that there is nothing wrong with these field lines. Alright, but the way to do it is, and I'm going to tell you this method, because electric field is a conservative field. Alright, so electric field is a conservative field. So suppose you take a charged particle, take a charged particle, and just assume for a second that the electric field is a closed loop. Just assume for a second electric field is a closed loop. Alright, so if it were true, let's say the electric field at all these points would be tangential. Okay, so the work done will be equal to QE dot dl. Alright, and I'm going to write a closed integral, because the closed integral of QE dot dl should will be the circulation of the electric field on this on this line. Okay, so if we find QE dot dl, now dl would be something like this. So E dot dl is always going to give me something positive. So QE dot dl at every point is going to give me something positive. So this will not be equal to 0 according to this one. Okay, but what we know is closed integral of E dot dl has to be 0, because electric field is a conservative field, and in a round trip the work done by the electric field has to be 0. Alright, so whenever we have to check if a configuration of field lines is correct or not, what we need to do is, if we can find closed integral of E dot dl, and if we find it not equal to 0, then certainly we can say that the conservative field, or the field line which has been shown, is incorrect. Alright, so that is what we're going to employ over here. So what I'm going to do is, I'm going to choose a loop like this, a rectangular loop like this. Let's say the length is L and the breadth is B. Okay, the field here would be E, and the field here would also be E, because they are equally spaced. We can assume that the magnitude of field is the same. Okay, now what will be the value of integral E dot dl at this side of this rectangle? That will be E multiplied by L. Alright, then at this point field is in this direction, and this circulation, or this length, is perpendicular to that. So E dot dl will become 0 over here. Now what about this one? dl would be this length. Okay, dl would be in the direction towards the left, and electric field is also towards the left. Alright, so again what we're going to get is E dot dl is also going to give me EL again. Alright, and again the electric field is perpendicular to the length, so it will give me 0. Okay, but the closed integral of E dot dl, which we have found for this loop, gives me 2EL, and which is not equal to 0. So certainly this kind of field lines is not possible. Okay, So option A would certainly be wrong. Option B is also wrong. And then let's look at option number C. Okay. So what do we have here is, so field lines are close at this instant, at this position, and field lines are separated at this position. Okay. So what we can say is the field could be E1 over here, and the field could be E2 over here, and E1 will be greater than E2. All right. And then again, what we can do is we can choose a loop like this. Let's call the length L and let's call the breadth P. Okay, so again what we're going to do is we're going to find out E dot dl, the closed integral of E dot dl. Okay, so at this, for this side, the closed integral would be E1 into L. This would be 0. And now the field is in this direction, but the length is going to go in this direction. So I'm going to get minus E2 into L. Alright. And then for this side again, I'm going to get 0. So what do I get? Closed integral of E dot dl. I get E1 minus E2 multiplied by L. So again, what do we see? That E1 and E2 is not same. So E1 minus E2 is not going to give me 0. So this quantity E1 minus E2 into L is not equal to 0. So again, option C will be incorrect. Okay, so the correct option would be none of these. Okay, and that is how you can find if a configuration of field lines is legitimate or not. Okay, so I have a question over here, but there is, in option B, there is only one direction, which is tangent to the curve. Right, you're right. But how do we define a tangent? All right, or how do we define a derivative? We define a derivative if the left hand side derivative and the right hand side derivative coincide. Okay, so not just that point, we also have to take infinitesimal steps to the left and to the right. And if we take that, we'll see that both of those are not going to coincide. Alright, so that is why even though there is only one direction at this point, we cannot say that they have the same direction, and this will be a legitimate field line. Alright, okay, so let's move forward. Let me take a new board. Okay, okay, so what do we have here? We have three concentric shells. Okay, a little bit difficult to draw. Nevertheless, I'm trying. Okay, so lousy drawing, but hope you understand. It's difficult to draw with this pen. Okay, so Q1, Q2, and Q3 are the final charges. All right, so they are the final charges. Now, what we have here is this part is Earth, and this shell is also Earth. All right. Now, how do we think about the charge distribution? How we think about the charge distribution is, first of all, if something is isolated, if a conductor is isolated, the charge on it is going to remain constant. All right. But what we see here is it is Earth, so the charge on it is not going to remain constant. So we will have to assume some charge, let's say Q1. Okay. Now, the charge here has to be minus Q1, because in order to have the Gaussian surface, if we take a Gaussian surface through this conductor, the flux through the Gaussian surface will be 0, and so the charge inside has to be 0. So if there is Q1 charge over here, there has to be minus Q1 charge here. Okay. But what we see here is Q2 is uncharged. Sorry, the second shell, has a net charge of Q2. All right, and it is an isolated conductor. So the net charge on it has to remain conserved. Okay, so if there is minus Q1 charge on the inner surface, there has to be Q2 plus Q1 charge on the outer surface. Alright, and again, this inner surface will have the opposite of this charge. Alright, and then the final charge on the outer conductor is Q3, and this is again not an isolated conductor. Okay, so the final charge has to be Q3 plus Q1 plus Q2. Alright, since it has minus Q1 plus Q2 charge on the inner surface, it has to have Q3 plus Q1 plus Q2 charge on the outer surface, so that this gets cancelled and the net charge on the conductor remains Q3. Alright, so this would be the charge distribution. Alright, now what we need to do is, again I'll have to grab a new board. Okay, now how would I get my equations? First of all, there are how many variables? There are 3 variables. Okay, so I have to form 3 equations. Okay, how do we do that? First of all, this is Earth. Okay, so if this is Earth, I can have an equation where I can find the potential of this shell, of the inner shell, and then I can make that potential equal to 0. Alright, so that will be my equation number 1. And then equation number 2 I can get from this outer shell. So what I'm going to do is, I'm going to find out the potential of the outer shell and then make that potential equal to 0. Alright, so let's do that. Let's do that over here. So I'm trying to form the equations. Okay. So let's write V1. Alright, so V1 is the potential over here. Okay. So how do you find potential? First of all, there will be potential due to this one, due to this charge itself, and that is going to be KQ1 upon R. Next, the potential at the inner shell due to the outer shell, that we can find out. So this Q1 and this minus Q1 get cancelled and the net charge on the second shell is Q2. Okay, now this point Q1 is inside this outer shell. Alright, so the potential will be KQ2 divided by 2R. So the potential of any point inside is equal to the surface potential. Alright, then what we can do is, now this outer shell, it has a total charge of Q3. So what we can write is KQ3, and since again this is an inner point, we can write it as 3R, because at any inner point the potential will be equal to the surface potential. Alright, so that is how we can find equation number 1. How do you find equation 2? I think we'll have to use a new board. Alright, or what we can do is, let's just get rid of this, because then I'll have to redraw the diagram. Okay, so I'm going to get rid of this and I'm going to write V2. Let's choose V. Okay, now what next I want to do is, I want to find the potential at the outer surface. Alright, since the outer surface is also Earth, its potential is 0. Alright, so let's quickly find that out. So the potential due to the outer shell will be equal to KQ3 upon 3R. That is the potential of the outer shell due to itself, plus the potential due to this shell. The potential due to this shell will be equal to, the net charge over here is Q2, so the potential will be equal to KQ2. Now this will be divided by 3R. Alright, why 3R? Because this point is outside this second shell. Alright, so in that case we'll have to take this distance from the center. That is equation number. So that is the potential at the outer shell due to the second shell. And then we'll have to find out the potential of the outer shell due to this inner shell, and that will be equal to KQ1 upon 3R. Again, because this point is outside of the inner shell. Alright, so that is also equal to V3. So because this is Earth, this will also be equal to 0. Alright, so we have two equations. One is V1 equal to 0, the other equation is V3 equal to 0, and the third equation will be, because both the potentials are 0 for shell number 1 and shell number 2, we can also equate V1 and V3. Okay. Alright. So again we have three variables Q1, Q2 and Q3. If we solve these three variables, you are going to get solve these three equations, you are going to get the values of Q1, Q2 and Q3. Alright. And then from there you can eliminate the options and you can find which one is the wrong statement. Okay. Again, I'm not going to spend time on the calculation. Let's use that time to understand some concepts, and the calculation part I'm going to leave it up to you. Alright, let's move ahead. There's no issue. I think some delay, some lag. Okay, let's move forward. Question number 21. Okay. Alright, so let's look at question number 21. So what do we have here? So a point charge is placed at 0, 0, minus a by 2 placed inside a conducting shell of radius a and center 0, 0, 0. Alright, so what do we have? We have something like this. Okay, so let's say this is the z coordinate like this. So this will be equal to minus a by 2. Alright, so I've taken the z axis something like this. Okay, so this is the origin. Okay, so this particle or the charged particle has been kept off center. Okay, so the flux linked to the hemispherical surface x square plus y square plus z square is equal to 4a square and z greater than 0. So basically, which hemispherical surface they are talking about? This hemispherical surface they are talking about. Alright, where z is greater than 0. Alright, so this the upper part of the sphere, that's what they're talking about. They want to know the flux linked to that. Okay, now the charged particle is kept over here. Okay, and where is, so let me redraw this. Probably this was not drawn very correctly. Let me redraw this with more. Upper part, this hemisphere they're talking about, the flux through that surface. Okay, okay. Now you might be tempted, you might be very well tempted to say that the answer is going to be q upon slightly less than q upon 2 epsilon naught. Why? Now suppose if the charge was kept at the center, okay, the charge was kept at the center, then through this entire sphere, the flux would have been q upon epsilon naught. Okay, so through the half hemisphere, the flux would have been q upon 2 epsilon naught. So now when it is displaced from the center, it is placed slightly off center. Okay, so what you would have been tempted to think is that the flux through this part would have been become lesser. Alright, now because this charge is closer to this surface, the flux to this surface would have been larger. Alright, but what we would have ignored is this conducting shell. Okay, so if there is a plus q charge over here, there will be a minus q charge on the inner shell, but the charge density is going to be non-uniform because the charge is being placed off center. Okay, but this conductor is neutral and this conductor is also isolated, so the net charge has to be zero. All right, so the outer surface there will be a charge of plus q, but this plus q charge would be uniformly distributed, and that is the difference. This plus charge is going to be uniformly distributed. Why uniformly distributed, and why does this happen is because the field inside the conductor has to be zero because of internal charges separately and because of external charges separately. So this field has to be zero due to this minus q and this q combined, and then separately the field also has to be zero by this plus q charge on the outer surface. Okay, so to make the field zero inside the conductor, this minus q and plus q, now this minus q gets distributed in a non-uniform fashion. Alright, but to get field inside the conductor zero, this plus q charge has to be in a uniform manner. Why? Because for a spherical charge distribution, only for a uniform spherical charge distribution, the field inside is zero. The field inside any point is zero. Alright, so to make field inside the conductor zero, this outer surface charge distribution has to be uniform. Alright, okay, now as a consequence of which the field outside or the field here, okay, and we also know that the field outside the conductor is only due to the external charges. The field outside the conductor is not due to internal charges. The internal charges combine to give field zero in the conductor as well as outside. So the outside the conductor, these field lines I am drawing, that those field lines are only dependent upon the charge on the outer surface. Alright, and this charge distribution is uniform, so the field lines would also be uniform. Okay, now if the field lines are uniform, the flux through this entire surface would be q upon epsilon naught, and since these field lines are have the field lines are uniformly distributed, or the field lines are absolutely radial in the outward direction. Alright, so half the sphere is going to get half the flux. So the answer has to be absolutely equal to q upon 2 epsilon naught and not less than q upon 2 epsilon naught. Alright, so that's where the concept of conductors comes in, and this becomes a very tricky question. Alright, but if you have your concepts right, now this again becomes a question which can be solved within 1 minute, but your concepts have to be very clear. Let me see if there are any questions. Alright, none so far. Alright, so let's move forward. Let me take a new board. Alright, and let's quickly try to wrap this up. Okay, question number 222. Again, this is a question on units and dimension, and I am assuming that nobody would have any doubt with this question. Alright, now let's move to question number 23. The question number 23, again, it's a very good question. Okay, so let me first draw this one. So this is the x-axis, this is the y-axis, and let's say this is the z-axis. X, y, and z. Okay, so the points are 2a, 0, 0. Alright, so this is 2a, 0, 0, and then the next point is 0, a, 0. So this point is that. So this distance would be a, and and then we have 0 comma 0 comma a. So that distance is going to be, so that point is going to be this one. All right. So the triangle formed is something like this. The triangle formed is something like this. Okay. So you see that it's inclined. This triangle will be somewhat inclined. Okay. Let me try and make that a little bit more clear. All right. And probably if I can use lines, I'm not sure if I can. Anyway, let me just try and, no, that's not what I intend to do. Yeah, I can join them with line. Excellent. All right. Perfect. All right. So that is the triangle I have. Okay. So we have to find the flux of electric field, and the electric field given to us is E naught I cap, 2 E naught J cap, and 3 E naught K cap. All right. Now what you could have done is, you have the electric field, and then how would you find the flux? Since this electric field is uniform, it does not depend on this, the x, y or z coordinates, it's uniform. So you could have found out E dot A. Alright, but in order to find E dot A, it becomes a little bit difficult because this surface is not parallel to any of the x, y or y, z or z x plane. Alright, so this is inclined to all the axes. Alright, so but if you know vectors, you could have found out unit vector perpendicular to this surface, and then you know the area already, and then you could have found out E dot A. Okay, but what we're going to use is, we're going to use a better method. Okay, and what that better method is, and probably you would know this. Suppose we have a surface like this, and the electric field lines are like this. If electric field lines are uniform, the flux becomes E multiplied by A projected. Alright, so the flux becomes electric field multiplied by the projection of the area perpendicular to the electric field. Alright, so the projection of this area, this irregular area, would be this area, and simply we can write flux as E into A projected. Okay, so all we need to do is, we can find the flux due to E naught I cap, and then we can find the flux due to 2 E naught J cap, and then we can find the flux due to 3 E naught K cap, and simply we can add all the three fluxes to get the net flux. Okay, so let's first start and do it for E naught I cap. So what will be the direction of E naught I cap? This is the direction of E naught I cap. It's along the x axis. Alright, it's along the positive x direction. So whatever this area is, if I have to find a projection of that area perpendicular to the x direction, it means I have to find a projection of this area in the yz plane. And what is the yz plane? This is the area in the yz plane. Is that right? Okay, so simply what is the area in the yz plane, or how I can write the flux due to the x component of the electric field, that will be equal to E naught multiplied by, now what is the area, this area, this shaded area, that will be half into base into height, and that is half into a square. So that gives me phi x. Now I want to find out phi y. So basically, what is the direction of electric field? This is the direction of electric field, and it's 2 E naught. Okay, so what is the component or projection of this area perpendicular to y-axis? So perpendicular to y-axis means it is in the zx plane, and if it is in the zx plane, am I dealing with this area? Okay, so I can write phi y as 2 E naught multiplied by, what will be this area? This area would be half, and what is the base? The base is 2a. The base is 2a over here, and multiplied by a. Okay, that will be phi y, and then we can find phi z. Now how is phi z? Phi z is like this. So we need to find a component of this area perpendicular to the z axis. And what is the area perpendicular to the z axis? It is the xy plane. Alright, it is the xy plane. So what area I am talking about? So I'm talking about, let me redraw this. So I'm talking about this area. Alright, this area in the xy plane. And how much would that be? That will be equal to 3 E naught, And what is the area? The area is half into what is the base? The base is 2a. And what is the height? The height is a. Alright. And that, if we add this phi x, phi y and phi z, that is going to give me the final answer. Okay. Another, a little bit complicated, the question was a little bit complicated, but if you get your concepts right, alright, if you get this concept right, then that becomes very easy and can be solved in a minute. Alright, so another very good question. Okay, let's move ahead. Okay, 24. So electric field between parallel plate capacitors is 2 Newton per coulomb and the charge on two plates are 10 coulomb and 3 coulomb. Then the force on one of the plates is, okay, so we have two plates. Okay, so the net charge on this one is 10 coulomb and the net charge on this one is 3 coulomb. But that does not mean that charge would be equally distributed on this surface and this surface. So what we already know is the net charge on both the plates gets distributed equally on the outer surface of the outer plates. Alright, so if this is 10, this is 3, 13 coulomb is the net charge on both the plates. On these surfaces, the charge is equal and opposite, so there will be no net charge. So all the charge will come out on the outer surface of the outer plates and will get distributed equally. Okay, so if that is 13 by 2, this is going to be 10 minus 13 by 2, so that is 7 by 2, and this is going to be minus 7 by 2. Okay, so the field inside is given and that is 2 Newton per coulomb. Okay, so can I say the field inside would be equal to Q upon A, and that is sigma into epsilon naught, that is the field inside between the plates of a capacitor. Okay, so that is going to give me 7 by 2, that is the charge, multiplied by area multiplied by epsilon naught, and that is given to me as 2 Newton per coulomb. Okay, but what we need to find out is, we need to find out the force exerted by this plate on this one. Okay, now let's talk about the force exerted. So the force exerted would be the field due to this one, the field due to this plate multiplied by this charge. Alright, so what is the net charge? The net charge on this plate is, the net charge on this plate is 10 coulomb. So can I write the field would be equal to, okay, or I can write it as, now because this is just one surface, what I'm going to get is 13 by 2, which is the charge, divided by A epsilon naught. Okay, but I have to divide it by 2 also, because due to just one surface, the field is sigma upon 2 epsilon naught. Okay, and due to this one, it will be 7 by 2 into A epsilon naught. But again, I have to divide it by 2. Why? Because the field due to just one surface is sigma by 2 epsilon naught. Alright, so this total gives me the same. Alright, if you realize, it will give me the same result. Okay, so that will be equal to, Anyway, we are back. Okay, let's continue. Okay, so if we were here, so what we said was the field due to this conductor at this point will be equal to 13 upon 2 epsilon naught into 2 due to this surface, and then 7 by 2 into a epsilon naught by 2 due to this surface, so that turns out to be 10 upon a epsilon naught. And then to find the force, we need to multiply it by the net charge. What is the net charge? The net charge is 3 coulomb. So this turns out to be 30 upon a epsilon naught. So we already know from here that 1 upon a epsilon naught is equal to how much? It is equal to 4 by 7. Alright, so let's substitute that over here. So this will be, alright, so you can, probably I can do the calculation on new board. So what? So what I got was 30 upon a epsilon naught, and then what do we have here? So 1 upon a epsilon naught is equal to 4 by 7. Let me check the calculation. Oh, sorry, this should be by 2 also. Yeah, okay, so this should be 15 upon a epsilon naught, not 30. This should be 15 upon a epsilon naught. So what we have here is 15 upon a epsilon naught, 15, and then 1 upon a epsilon naught, we can substitute it by 4 by 7. Alright, so this will become 15 multiplied by 4 by 7, and that is going to give us 60 by 7 Newton. Alright, and that should be answer. So you should, the correct answer should be option C. Alright, let me know if there's any difficulty and we can move along. Okay, so let's move to question number 25. So what do we have in question number 25? Force experienced by a semicircular rod charged with a charge Q placed as shown in the figure of the wire. Radius of the wire is R, and infinite light line of charge with linear charge density lambda is passing through its center. Okay, so what do we have here? We have a rod infinitely long. Okay, and then we have a semicircular ring. Okay, and that is also charged. Okay, and what is the charge density? Okay, so we have been given charge Q, and this rod is charged with lambda. Okay, so we need to find the force exerted by the semicircular rod. Okay, so we need to find the force on this semicircular ring due to this infinitely long charged rod. Okay, so this again is not a very difficult question. Okay, but the thing here is, what we need to understand here is, uh, okay, so due to we certainly know the field due to an infinitely long uh, uh, a linear charged rod. All right, so a linear charge distribution, we already know the field, so that field is equal to 2k lambda divided by r. Okay, and we also know that the field would be radially outwards. Alright, so the field would be radially outwards. So what I'm going to do is I'm going to redraw this in a manner which would be better to visualize. Okay, so how it would be better to visualize is, let's make the ring like this and let's make the rod go like this. Alright, so this rod is perpendicular to the plane of this paper, the plane of the screen, and the ring is like this. Alright, so basically I've just rotated this rod by 90 degree. Okay, now what I know is that the field at any point, the field at any point, so let's say this angle is theta. Okay, so the field at any point would be radially outwards, and what will be its value? Its value would be 2k lambda by r. Okay, now you do realize what we need to do here is we have to take small elements. Alright, find the force on that and then find the net force. Okay, so at an angle theta, we're going to take an element d theta. Okay, so what will be the length of this element? The length of this element is going to be r d theta. Okay, so what will be the charge on this small element? So how do we find dq? Dq we find as charge per unit length. So what is the length? The length is pi into r. So charge per unit length multiplied by the length. So the length of this small portion would be r d theta. So this becomes what? This becomes q upon pi into d theta. Alright. Okay. So the force experienced, would be equal to dq multiplied by the field. Alright. Now what we are also going to do is we are going to take a symmetrical element over here. Okay. Why do we take a symmetrical element over here? Because the force is a vector quantity. Okay, so if we're adding all these forces, we have to add them vectorially. We cannot do a direct addition of all these vectors. Okay, so the better way to do it is resolve it into components, and all those components then will be in the same direction, and the components in the same direction can then be added directly. Okay, so we have f over here. So what we're going to do is we're going to resolve it as f cos theta and f sine theta. Okay, again this would be f cos theta and this would be f sine theta. Okay, so the net force, alright, so what we see is this f cos theta here and f cos theta here will get cancelled. Okay, so what we see is only the vertical component of the force is surviving, the other components are not surviving. Alright, so what can we say? We can say that the force, the net force that we have to find out, the net force we have to find out would be equal to dq into E, which is the force, and only the vertical component, which is sine theta. Alright, and that we can write it as, what is dq? dq is q by pi into d theta. What is the field? The field is 2k lambda by r. And then what is sine theta? Sine theta we can certainly find it from this triangle. So sine theta will be equal to the perpendicular divided by the hypotenuse. So how can you find that out? Or we can simply write sine theta, there is no issue. So we can simply write sine theta because my integral is going to happen in terms of d theta. Alright. So this is the term dqe sine theta, and we need to integrate it from 0 to pi. Alright. So that is going to give me the net force. Alright. So this integration is not very difficult, and I hope you can follow this integration, and then you can look at the options and find the right answer, and the right answer is going to be B. Okay, so again this is the concept, and the the calculation part, I'm going to leave it up to you. Alright, so I hope that is clear. Also, let's move ahead. Only a few questions remaining. Let's quickly go through them. 26. Okay, so a charge is distributed uniformly in xy plane with charge density plus sigma. Okay, so here there is plus sigma charge, and on the rest of the three quadrants there is minus sigma charge, and the particle is taken from 00d to 002d. Alright, so basically it is going out of the plane of the screen. Okay, from distance d from the surface to a distance 2d from the surface. Alright, now we know that for an infinitely large plate the field is a constant and it does not depend upon the distance, and that field is equal to sigma upon 2 epsilon naught. We know that already. Okay, but the problem here is this is not the same charge density throughout. Okay, so the charge density is minus sigma over here and the charge density is plus sigma over here. Okay, now how do we solve this? It becomes a little bit tricky. Okay, but we need to think a little bit in terms of symmetry. Okay, how do we think it a little bit in terms of symmetry is? Okay, I'm going to give you an example. So let's say this is the plate. All right, this is the plate. Okay, and we are talking about a point over here. So infinitely large plates means that it extends on all sides to a very large distance. Okay, so we can say that whatever is the amount of plate above this point is the same as the amount of plate below this point, is the same as the amount of plate left to this point, and is the same as the amount of plate right to this point. So what then happens is, so if we consider any symmetrical elements, okay, any symmetrical elements, the field would be like this, and due to this one the field would be like this. Okay, so what will be the resultant field? The resultant field would be like this. And similarly, if we take any point over here and a symmetrical point over here, the field would again be, the resultant field would be along this. Alright, so because of this symmetry the net field is always perpendicular to this surface. Okay, now let's consider this point. Now if this positive charge is replaced by negative charge, just assume for a second that this positive charge is replaced by a negative charge. Now again what we understand from here is, if it was all negative charge, it was all negative charge throughout. Okay, so the field would be, again, can I rub this off? Let me redraw that again. So if it were all negative charge, okay, so the field at this point would be like this, correct, towards, okay, and this will be equal to minus sigma upon 2 epsilon naught. So basically minus is just telling you the direction of the field. Okay, now understand this, that this field is only the resultant of the components which survive perpendicular to this surface. All right, all those surfaces, let's, for example, let's say this point and this point. So the field would have been in this direction and the field would have been in this direction. Okay, so the component of that field would be in this direction and in this direction. So this field, the resultant field, is only there because of the contribution of these field, the components of these fields along the direction which is perpendicular to the surface. All right, so if we keep that in mind, basically what is happening is, this surface, this negative charge over here and this negative charge over here. Okay, uh, let me redraw that again. So this negative charge over here and this negative charge over here. Alright, they will have a field in this direction and they will have a field in this direction. Okay, but what it is going to do is, it is going to have a field perpendicular and it is also going to have a component which is not along this direction. Okay, but we are only concerned with the direction of, or the component of the field which is perpendicular to this surface. Okay, now if they were all negative charges, if they're all negative charges, the contribution of each quadrant would have been 1/4. All right, the contribution of each quarter would have been 1/4. So that would have been sigma by 2 epsilon naught by 4 due to this quadrant, due to this quadrant, due to this quadrant, and due to this quadrant. Okay, so for a moment, let's just forget about this quadrant. Let's just forget about this quadrant, and let's just forget about this quadrant. So this is negative charge. This is negative charge. So what will be the force? What will be the amount of field? The amount of field would be sigma upon 2 epsilon naught, and how much? 1 by half. Okay, so quarter contribution from here and quarter contribution from here. Okay. Now what about this? Now let's talk about this negative charge and this positive charge. Okay. So if they were all negative charge and negative charge, the field would have been again in this direction. But there is negative charge and there is positive charge. So there will be equal magnitude of contribution for the electric field, but that will be in the opposite direction. Alright. So there will be no field. So there will be no field due to in this perpendicular direction due to this positive charge and this negative charge. So what will be the net charge? The net charge is going to, or the net field is going to be sigma upon 4 epsilon naught. Okay, that will be the net field. And what is the direction of the field? The direction of the field would be towards the surface, all right, or towards this charge plate. Okay. Now the question here is, what is the potential difference? All right. So the how do we find the potential difference? If the field is uniform, the potential difference is given as V is equal to ED. Okay. One thing we should also consider is, because of this asymmetry, there will be field, or there will be a component of field parallel to the surface. Alright, there will be a component of the field parallel to the surface. But how is the object being displaced? The object is being displaced again perpendicular to the surface. Okay, so this component of electric field will not have any contribution to the potential difference. Okay, so all the potential difference that is going to be between these 2 points has to be due to this component of the field. Okay, and which we have found out to be this. Alright, now the field is in this direction and the displacement is in this direction. So basically we are moving opposite to the field. Alright, so basically we are moving opposite to the field. So if we are moving opposite to the field, or so we are moving from 00D to 002D. Yeah, so if we are moving opposite to the field, then the potential difference is going to be increasing, or the potential is going to increase. Okay, so what will be the potential? The potential will be equal to, so the potential will be equal to sigma upon 4 epsilon naught. Okay, sigma upon 4 epsilon naught, that is the field multiplied by the distance. And what is the distance? Oh, sorry. We have to calculate the work done by the electric field. Okay, so the work done by the electric field would be the negative of. Okay, so if we have to calculate the work done by electric field, we don't have to worry about the potential. Okay, let me get rid of this. So if you have to calculate the work done by the electric field is in this direction and the displacement is along this direction. So the work done will be equal to minus the field into Q is going to give me charge and then multiplied by the displacement. Alright, so A has to be the answer. Alright, a slightly complicated question. It sort of you have to be very well versed with the symmetrical aspect of this one, and but the concept is pretty good. Alright, this question is one of the best questions in this paper. Okay, but again, if you understand this concept very well, it is not a tedious question. Alright, if you get this correct in your head, you can solve it very quickly. Alright, okay, so if there is no issue, I can move forward. Okay, let's go to question number 27. So what do we have here is, an electric dipole is kept on the axis of a uniformly charged ring at a distance r by root 2 from the center. Okay, so let's say this is the ring. and the dipole is kept on the axis. Alright, let's say this is the dipole. Okay, the dipole moment is P, and then this distance is R by, sorry, this distance is R by root 2. Alright, and naturally this distance will be equal to R. Okay, so what we need to find out is, we need to find out the force on the dipole. Okay, we need to find the force on the dipole due to this charged ring. Okay, uh, what we can do here is the opposite also. We can find the force on the ring due to this dipole, and that will be equal and opposite. Okay, so we can do it either way, and this one would be easier. Why? Because we already know the field due to the dipole, and when we know the field due to dipole, we can multiply that with the charge, take care of the force and the components, and then find the net force. Okay, but if we would have to do it the other way around. So because of this charge, we might have found out the field. Okay, but this would be minus q over here, and this will be plus q over here. Okay, so then we'll have to find the field over here, then find the field over here, and then subtract those two fields, and then take into account that the length of the dipole is much less than the distance between them, and then we'll have to solve it. Okay, so this might become a little bit complicated, and we don't want to do that. Okay, so what we want to do it is, how we want to do it is, find the field due to this dipole at this point or at all those points, and then do a vector summation. Okay, so first let's try to find out the field. Okay, how would we find out the field? Okay, so what is this distance? This distance from the center of the dipole would be r square or basically what we can do is, what we can do is alright, so anyway we need to find this distance. Alright, so this distance would be equal to r square plus r square by 2 and under root of that. So that is going to give me, root 3 r by 2. Okay, so this distance here, let's call that small r, is equal to root 3 r by 2. So I'm trying to find the field over here. Okay, so how do we find the field over here? The field has two components. Okay, this is the radial component of the field, and then there is the tangential component of the field. Okay, the radial component of the field ER is given by, or we can find the field directly. So the field is equal to Kp by r cube, then under root of 3 cos square theta plus 1. Okay, that is the field. So if this angle is, let's say, alpha, what is theta? Theta is the angle it makes, this r vector makes with the dipole axis. Alright, so this theta will then become pi minus alpha. Okay, so the net field over here would be Kp by r cube and then under root of 3 cos square theta. So basically cos pi minus alpha, so theta is pi minus alpha, so I can write cos pi minus alpha as minus cos alpha, minus cos alpha. So that is going to give me 3, but this is a square, so it does not matter. Okay, so it is going to give me something like this. But we are interested in the direction. Okay, we are also interested in the direction of this field. Okay, so the direction of the field, let's say this is the resultant field and this is the radial direction. Let's call it something else. Let's call it beta. Oh, sorry. Okay, so what do we know? We know that tan beta is equal to tan theta divided by 2. Okay, so in this case, what is tan theta? This angle. Okay, so that will be equal to what? That will be equal to r upon r by root 2 and then divided by 1 by 2. So this is going to give me 1 by root 2. Alright, I think it has become a little bit lousy over here. Let me take a new board. I think it got stuck again. Just a second. So here is the dipole. Okay. So if we find this angle tan alpha, this tan alpha is equal to r upon r by root 2. Okay, so that is equal to what? That is equal to root 2. Okay, then what do we say if this is the radial direction and then this is the tangential direction? So if the field is like this, okay, and this angle, let's call this beta. Okay, if we try to find this angle beta, so tan beta is equal to tan theta by 2. Okay, so what is tan theta? So tan theta would be this angle, so which is root 2. So root 2 by 2 is going to give me 1 by root 2. Okay, so what does that mean? If this angle is beta, this angle is 90 minus beta. Alright, so if I have tan beta is equal to 1 by root 2, then can I say that cot beta will be equal to root 2? Okay, so what does that tell me? That tells me that this angle alpha and this angle will be same. Alright, you get that? This angle alpha and this angle will be the same. So what will happen in reality is, what is going to happen is, so because of this dipole over here, the field at this point will become perpendicular to the dipole axis, and field at this point is also going to be perpendicular at this axis. So at every point of the ring, the field is going to be perpendicular to the dipole axis. Okay, so if the field is like this, and because it is equidistant from distant from all the points, the magnitude of field will be the same, and it is all radially outwards with respect to this ring. So what will be the net force? The net force in that case will become 0. So the correct answer will be 27. For the 27 will be D. Alright, again, slightly tricky question, but if you do it right, then you will certainly arrive at the right answer. Okay, I hope everything is clear till now, and then we move forward. Okay, so in the interest of time, I'm not going to spend time on question number 28. I'm just going to give you a hint. Okay, so basically the field is in the x direction. There is no field in the y and z direction. Okay, so you are only concerned about this surface over here, which is perpendicular to the x-axis, and this surface here, which is perpendicular to the x-axis. Okay, so at the x coordinate, which is 0.1, you can find the field and then multiply that by area. That will be the flux, and that will be negative flux because the area vector would be toward negative x-axis. Okay, and then at this point you can find the field substituting x is equal to 0.2 and then multiply that by area, and then you will get the flux. Okay, add those two quantities and then you will get the answer. Okay, so I'm not going to spend much time over here. So it is mostly straightforward. Okay, let's quickly look at question number 29. So what question number 29 tells me is, again, this is again a very good question because it only requires your thinking and no need of a pen. Alright, so this point is A over here and the field here is E. Alright, so this point, this distance from here is Z naught. So the field over here is E. Now what they are asking is, due to this same configuration, alright, what will be the field at this point? That is the question. Okay, so uniformly charged hemispherical shell of radius r, if field at A, which is this point, is E, which is a vector, and the field at point z0 0 0. So symmetrically, if we take a point here, then the question is what will be the field? Okay, how we should think about is, let's cover this up. Alright, let's take another identical hemispherical shell and cover this up. If we cover this up, what will happen? What will be the net field at point A? The net field at point A will then be 0 because inside the uniformly charged hemispherical shell, the field is 0. Okay, so can we say, let's call this part 1 and let's call this part 2. So the field due to 1 plus the field due to 2 is 0. Can we say that? Alright. Okay. Similarly, let's think in terms of this one. Okay. Assuming that this part 1 was not there. Assuming this part 1 was not there. Okay. So if only this spherical surface would have been there, or if only this hemispherical surface would have been there, what will be the field at this point? The field would at this point would be the same as this field E, because this condition and this condition is the same. Okay, so what we need to think here is the field due to the part, the first hemispherical part, and field due to the second hemispherical part are equal and opposite. That is why they cancel out, and this becomes, the field here becomes 0. Okay, so due to this hemispherical portion, the field at this point would be something in this direction. Okay, and equal in magnitude to E. So the field due to this first portion would be equal to in this direction and equal to E, which is given to us. Okay, now just consider the symmetry. Okay, so what we have found out is due to this spherical shell, just now only consider this spherical shell now. Alright, so if you consider only the spherical shell, the point at this point, the field is how much? The field is E. Is that correct? Okay, now just think about this hemispherical shell. And due to this hemispherical shell, it is asked what will be the field at this point. Okay, so if you observe symmetry, the field here would be E. Alright, and now what is the direction of this E? This E is the same direction as this E. Alright, so what will be your answer? Your answer will be C. Is that clear? Another very good question, just requires your thinking and no pen work at all. Okay, I hope that's clear. Alright, so finally, let's look at the last question and then we'll be done. Okay, so the last question is on vernier calipers, and again it's a straightforward question. Okay, how do we solve for vernier? How do we calculate the least count for the vernier caliper? The least count of the vernier caliper is defined as 1 main scale division minus 1 vernier scale division. Alright. That is how we find out the least count of a vernier calipers. Okay, so main scale division is 1 millimeter, and 20 equal divisions on the vernier scale match with 16 main scale divisions. Alright, so basically I can write 16 MSD is equal to 20 VSD. Alright, so I can write 1 VSD will be equal to 16 upon 20 MSD. Okay, and that value I can substitute it over here, so the least count will become 1 MSD minus 16 upon 20 MSD, so that is going to give me 21 MSD divided by 5. Okay, so what is 1 MSD? 1 MSD is 1 millimeter, and that divided by 5 is going to give me 0.2 millimeter. Alright, so D will be your answer. Okay, so I hope this helped, and you're going to go and revise it and rectify your problems. And if you have issues, you can mail us and we can cater to that. Alright, it's been a long session, so take a bit of rest and we'll see you after the next test. Alright, all the best. Bye bye.